We still have 2 more questions.
Okay, that's all right. You can write down the answers as we get to them. Don't worry about it. That is the thing. All right, so we did this one. We did this one and we did this one. And you guys watched your videos. All right, so let me make sure this is turned on because we're gonna run into the next. Okay, can y'all pause that one over there so that we can hear? Let's do it later. Drew, pause that. Drew, pause it. Okay, let's go through some of these. These are your, so you guys, if you did the lab, you get a complete for it. So let's see what kind of answers you guys got. How about for this first one? What country was Chernobyl located in?
USSR.
Ukraine.
Ukraine today, USSR at the time, correct. All right, and then what was the closest country?
Belarus, but at the time, Russia.
Yeah, it was all part of the USSR at the time, but Belarus, they're right on the border of Belarus, right? Okay, and then, so that obviously was pretty scary for people hanging out in Belarus. And then how about when you got to the questions about the article, the Britannica article, so which union of countries did they belong to? We said it.
Yes.
USSR. Let me ask you, in 1986, who was president of the United States? Oh gosh. Say it.
What?
Say it.
Ronald Reagan.
Yes, Ronald Reagan. Ronald Reagan was president of the United States in 1986. Who was the leader of the USSR?
Gorbachev.
Mikhail Gorbachev, correct. And when you got to one of the YouTube videos, did you guys hear the name Boris Yeltsin mentioned? Cole, shush. Did you hear the name Boris Yeltsin mentioned? Okay, now Boris Yeltsin is the man who, Drew, is the man who succeeded Mikhail Gorbachev. He was the next leader, okay? And what was going on at the time, I said it at the beginning, is we had this whole Cold War thing going with Russia, right? It was, or USSR, it was pretty scary. So you have the Soviet Union, and then how many reactors were there? 4, okay. 3 were in use, there were 4, correct. All right, now, what caused the disaster?
Cheap.
Cheap equipment.
Cheap equipment, what else? Stupidity.
A very bad testing.
Testing.
It was a test to see if the reactor could.
So technicians at Reactor 4 attempted a poorly designed test to see if the reactor could be cooled if a power failure occurred. And that caused the reactor to become unstable. Cole, hush. Cole, hush. All right, so then, and how did the Soviet government react?
Oh, they should have covered up because they're going to be.
They did. Why'd they do that?
Sorry?
Exactly.
Well,
Hush and pay attention.
He's right here.
He lives here. How did the Soviet government react to the disaster?
They said
Ethan.
there was.
They said there wasn't any issue.
Yeah, there wasn't any issues. There wasn't as much radiation as
Because
there was.
they didn't want to be a national embarrassment.
Right. So they did evacuate 30,000 people, but then they attempted to cover it up. And then they eventually admitted that there was an accident, and they started burying debris to prevent further spread. Why would they cover it up?
Because it was an embarrassment.
It is an embarrassment. Yeah, it was a huge deal. Mm-hmm.
Or yell at.
Right, exactly. So then, what were the consequences of the explosion?
Radiation,
Radiation.
death.
Lots of terrible things. Yes. So basically, you had illness in the local population, and the land is now unusable, right? Thousands of people had to leave their homes. Radioactivity spread over all of Europe, and then contaminating crops and livestock in other countries that had nothing to do with this. And then how about, see, I love these creepy old pictures. You can find
Is
blogs.
it possible to live there?
Nope.
No.
Dang.
But you can find, because she thinks the creepy's cool. I agree. There are wonderfully done like photography blogs that have all these pictures of Chernobyl today that are spooky and creepy, and they're really interesting to watch or look through. So you watch these 2 scenes. All right. And then what do we get from them? So why did the Soviet Union try to hide it? We talked about it, to protect the security interests of,
Also, like,
Sorry about my
if they're in the Cold War, and if the communists weren't able to like maintain a factory, how are we supposed to be intimidated by this factory?
Exactly. The Cold War had a lot to do with who had the nuclear weapons, who had the big bombs. And if these guys can't even manage a reaction in a nuclear reactor without causing a problem, that made them look really bad on the global scene. And it was all about maintaining their authority, maintaining their power, maintaining, fear over everyone. That was what they were trying to do. So why did the government think that the level of radiation was much lower than it actually was?
Because the measuring devices only went to a certain level.
Yeah, so the meter had reached its maximum. Even though in practice, the level was way higher, right? Way higher. All right, and then you watched this last video here with Banana Dude, right?
Banana dude.
I love Banana Dude. So why does he use a banana to compare radiation levels in the places he visits? Because bananas have a little bit of radiation. And so because a banana has a small amount of radiation, and the reporter wanted to illustrate the high radiation exists in all the places that he visited. So of all the places he visited, where was the highest radiation found?
That basement, I think, right?
Chernobyl was the basement where the firefighters' clothes were left. Yep, very good. Okay. So what was this last question was, one of the last ones. How is it possible to walk around the streets of Chernobyl today despite the high level of radiation?
Security measures.
Very, very qualified scoring agencies that take very good preventative measures to keep their people safe.
That, and also Russia collected all the topsoil in the area and dumped it elsewhere. So that dropped some of the pollution.
It still is radioactive.
It still is, correct. And you have to wear the right kind of gear. That's right.
What is that radioactive topsoil?
That's don't ask questions like that, Alex.
Get it or anything.
So I wanted to show you guys a couple of real quick things before we wrap up for this lab, even though you guys are already into another class. But this is how, wait a minute, this one? This is how we found out. Now, 1986, ask yourself this, were your parents alive? How old were your parents?
I don't know.
I was
My dad's
10.
50, almost.
Mhm.
I think might not be alive.
Yeah, I was 10 years old when Chernobyl happened. So most of your parents were probably your age or younger.
I was 5.
And yeah, so, no, her mom.
I said you were
I wasn't
5.
alive in 1986.
So this is what,
Like you're talking about?
so this is what we all heard.
Nuclear power. Massive quantities of radiation have apparently been released in an accident at the Chernobyl power station in the Ukraine. Many thousands of people live in the vicinity. Moscow admits there have been casualties, and signs are that a big relief operation is underway. This report from our European correspondent, Mark Colvin.
In an unprecedented step, the Kremlin acknowledged there'd been an accident, but only after Scandinavian scientists had picked up high radiation levels.
That's not the voice coming out of that person.
The Soviet Council of Ministers of Red October, sign of the degree
Yeah.
Moscow's concern. Diplomats speculated that the mention of casualties could indicate a high death toll. The Soviet news agency TASS said one of the reactors at Chernobyl, north of Kiev, had been damaged, but there are no details of how serious the accident was. Soviet nuclear plants like this one we were given a rare opportunity to see in 1984 have less built-in safety precautions than Western plants. TASS said measures were being taken to help the injured, and the government was setting up a commission of inquiry. Reports from Kiev say all bus services in the city have been cancelled. The vehicles are being used instead to evacuate the Chernobyl area, with a population estimated at around 50,000. The wind blew a cloud of radiation over the Baltic states towards Scandinavia. Some radiation monitors recorded levels 10 times above normal. In Sweden, about 600 people were evacuated from a nuclear plant north of Stockholm. Authorities there thought at first the radiation levels must be coming from a leak in their own reactor. Some Western scientists suggest the type of pollution detected could indicate a nuclear meltdown.
Enormous amount of radioactivity must have gotten out of the power plant. And I spoke with some people in Sweden this morning, and they indicate that they have found iodine in Sweden and cesium, which means, which very strongly suggests that there was a core meltdown.
The accident at 3 Mile Island in the United States in 1979 was a partial meltdown. The nuclear rods melted and fuel pooled at the possibility that the pressure vessel ruptured, leaking a vast cloud of radioactive steam. And one big problem which Western scientists see in Soviet plants is the lack of a containment building. When all else fails, there's no outer shell to hold the radioactivity in.
So that was not a fabulous thing to have happen. Eleanor, you may want to check and see if your ride is here just because it's time for you. But so we'll watch these other ones though. This was what we got here in the US not long after. Yep.
Fairly clear detail on what's going on at the Chernobyl nuclear reactor.
And it took
Boris
a while.
Yeltsin, who's the Communist Party chief in Moscow, told West German television the accident was caused by human error, but the area around the reactor is
Blame the
still
workers.
radioactive, too dangerous for people
You
to
don't
enter,
care if it was
and
their
some of the
fault.
neighboring reservoirs are
Did a little pressure
contaminated.
from above.
Yeltsin said that helicopters are dropping lead and sand and neutron-absorbing boron on the reactor site. This information will help the West further understand the problem. The Reagan administration said again today the Soviets have not been helpful enough. Here's ABC's Steve Shepard.
Vice President Bush strongly denounced the Soviet Union today for concealing details about the Chernobyl disaster.
It is unconscionable in this, with this tragedy there, that they are not coming forth in a new spirit of frankness and openness.
Other officials say that lack of candor may explain why so few in the West believe the low casualty figures the Soviets have been claiming, figures that may in fact be accurate.
It's entirely possible their answer is correct, or it may not be, because the data we have just doesn't permit pinning that number down.
But some are known. U.S. officials say airborne radiation from Chernobyl now covers much of Europe and the Western Soviet Union. Aircraft have detected some radiation 400 miles west of Norway. In Eastern Europe, the situation is worse. U.S. travel advisories are still in effect for the Kiev region of the Soviet Union, and today there were new warnings about Poland.
We are recommending that women of childbearing age and children should not travel to Poland until the situation is clarified.
In parts of Poland, radiation levels earlier this week were very high. At this lake, some 500 times above normal. Polish officials continue to distribute iodine foods to children and to warn citizens to wash fresh food and avoid drinking milk. With winds now blowing to the south, Romania today declared a state of emergency and told its citizens to remain indoors. In Washington, the Environmental Protection Agency said the U.S. doesn't appear to face any health threat, since atmospheric radiation is not expected over the U.S. before this weekend, if ever.
The longer the time, the less likely it is that we will see any detectable levels of radiation in the air mass move over the North American continent.
U.S. officials are still not certain whether the reactor fire at Chernobyl is extinguished or continues to smolder and produce radiation. Either way, the EPA calculates that at one time, radiation levels at Chernobyl were high enough to cause severe trauma, including death. Steve Shepard, ABC News, the Pentagon.
There's a lot of uncertainty, as you can tell.
ABC News is old.
Yeah, man. A lot of uncertainty, and we didn't know what was going on. And I won't show you the Gorbachev one, but you can imagine, I mean, he says pretty much what you think he's going to say. Is this just this sort of business?
The accident, he told his countrymen, has now claimed 9 lives and injured 299 others.
Only 9?
He tried to explain what went wrong.
The power of the reactor suddenly increased.
Mm-hmm.
There was considerable discharge.
It's Gorbachev being Gorbachev, who was not, he wasn't the worst guy in the world. I mean, he wasn't a great guy either, but Reagan and Gorbachev had a relationship that was very interesting, and Reagan managed to get the Cold War ended, and it was because he had to deal directly with Gorbachev. But I wanted to show you one other quick thing before we move on to the lesson.
Hiroshima.
Yeah. So if you make an atomic bomb as opposed to a nuclear reactor, you get this. This is Hiroshima. So this is World War II, and this is basically how it ended. Get bigger, don't get bigger, be weird, I don't know.
This is all fake footage, right?
No, this is footage.
They actually had like cameras like this.
Well, they had cameras, but as you can see, they're not great cameras. And that's what it left. Nothing, just nothing.
Problem.
Mm-hmm. It was terrible.
Yeah.
Yeah, it was pretty terrible, as you can imagine.
Don't support Nazis.
And this is what, true. So this is picture of Nagasaki bomb, and this is the sort of stuff left behind. I mean, it leveled.
Is that a Buddha?
That is Buddha.
I mean, it's crazy how we just create just weapons of mass destruction.
Yeah.
Like, we could be creating other things, but the U.S. back there, like, nah, let's create something that'll just level an entire city.
Mhm.
An interesting statistic I heard though was, as bad as that was, it debatably saved a lot more lives because the war could have kept going.
Yeah, there's always going to be that question, but that was the reasoning at the time.
Yeah,
But anyway, we won't get into the politics of it. Real quick, this is the amusement park at Chernobyl, how it looks today.
What is an amusement park?
Yeah, isn't that wild?
There's an amusement park there.
Uh-huh. And this is the hospital in Chernobyl, how it looks today. Doesn't that look like a place you want to go? So not creepy at all. And this is actually a kindergarten in the school, in the elementary school in Chernobyl.
Okay, wait. How is this like a whole living institution thing? Or
No, they just had nap time, I think.
They had a
These are-
kindergarten, they had an amusement park.
It was a town. Yeah, it was a town. These are actual pictures from Chernobyl today, and they're uber creepy. I mean, uber creepy, right?
All the state are nuking that.
I mean,
No, why?
I think this stuff is fascinating. This is what I mean by their incredible photo blogs, where people found just the right weird things.
Didn't we see the Enola Gay?
We did see the Enola Gay, yes.
Yeah, that's the Enola
The
Gay.
Enola Gay that dropped the atomic
At
bombs
some point, I guess too.
is at the Smithsonian Air and Space in outside DC.
I saw it. All of it actually.
Look at the swimming pool.
Okay, wait. I have a question.
Don't know where the water is.
Hang on, I can't.
Yeah,
Cole,
that's
Cole,
safe. That's
hush,
safe.
Cole.
Yes.
Sit it. Yes, Shannon.
Why would they think like having this big like gym and everything when they have like a power plant right there?
Well, there's power plants everywhere.
Well, yes,
Yeah.
but like
It was just a part of that was their village. That was their livelihood.
they're like a YMCA.
Yeah, they had everything. Everybody lived there.
Huh.
Like, look at creepiness. This is creepiness. But I love these pictures. They're great. I mean, it's frozen in time.
It's kind of like Harry Potter mixed with the zombie apocalypse.
Yeah.
Yeah, I guess so.
Yeah, there you go. Look at this.
Mixed
Look at this.
with
See the
Jurassic
store.
Park. Oh, as a horror movie.
I love these. I think they're fascinating.
It's really interesting.
Mm-hmm. It's a mask, like a gas mask.
Oh my god, those are creepy. Oh well.
See, people have gone through there and found weird things and posed them for weird pictures, which make it even weirder. To see the grass all growing through and the bumper cars.
Everything's how it moved it forever.
Yeah.
So funny games, so you see a gate like that.
And you can look at it on Google Earth. You can zoom in.
Yellow
It's
seats.
pretty cool and see the pictures. It's really interesting. But it is just like a total
Doesn't
ghost
make you
town.
feel safe that at least we have this.
And it's we did have like a partial meltdown at 3 Mile Island here in the United States. And let me ask you this, are there nuclear reactors that you could drive to and see from here? Oh yeah. Lots of them. Not hard to find, actually. There are, that's a good one. Woo! Maybe that's the head. Maybe the head belonged to that one.
What is
But,
that? What is it?
it's a kid bouncing on a ball. So, yep, it's interesting. But yeah, people like to take weird pictures.
It's interesting to me.
Yep,
Oh, that looks like.
I love that one.
That's pretty cool.
I like that one.
All right, so
This picture
so-
that was like the bus or
This?
something. It's the
Oh.
Magic School Bus.
yeah, Magic School Bus went bad. Yep,
And there we go, communist.
that's the Soviet seal. Mm-hmm.
That's the communist.
There's the school. Look at the books still on the desks. Like,
Everyone was like in the middle of
Time to
lunch,
go.
They heard that it was coming and they were like, nope.
all right, so juniors, you guys can go get your lunch before Miss Jackie gets here. Y'all go do that.
Okay, cool. I look up
This is the science lab in the high school.
That's the very first thing that showed up. Let's do it.
Drew, go ahead. And are y'all ready for your class then? Y'all can come on up. Or you can stay there if you want. I don't care. Anyway,
Dude, that was just the nation's flag.
That's a great one.
Oh,
I don't know what's up there. That's pretty awesome. Yeah, no swimming. Definitely no swimming. Coffee shop. Yep. Spare room for ghosts, it says.
quite a few spare rooms. Hospital.
Like the children's ward in the hospital. Ugh. Creepy.
You want a what? Capital.
Look at that one. Very cool. Yep, a random fox. Who probably shouldn't be there. In the movie, in the docu-series, that's one of the worst things is they were shooting the dogs and stuff because they knew they were going to die a miserable death and people were shooting their dogs and stuff.
Well, the biggest part is that they didn't want the dogs leaving the zone.
Yeah, they didn't want them coming out and bringing it. So, yep. That's the sarcophagus right there. You probably saw that when you were looking at stuff today.
There was something about being a big mass of radioactive stuff still there.
These folks are still hanging out for whatever reason.
This is never leave home.
It says, although it's forbidden, some people still live nearby Chernobyl. About 150 people decided to come back to home and farm their land. They believe that the radiation today is lower than the one they were exposed to, so it can't harm them. The returners grow vegetables and eat them, despite the warnings that food in the exclusive zone is lethal. But for them, that area is their home, and they always return to it. So, you know? Yep. Let's see. We should have, I think, Jack and Michael over here. Jack says World War II is his favorite time period to learn about.
Oh, that's my favorite too.
And the doll needs a Snickers. Yeah, that doll needs more than a Snickers, Jack. That doll needs so much help.
He's not gonna be able to sleep.
So much help. Yeah, I don't know, man.
Favorite time period to learn about.
So Jackson.
All right, so let me get this going for you guys. Yeah, Jack's home today. And Michael is too. I don't know if Michael's going to join us or not. I don't see him yet, but he might still. Can you please move? I'm trying to move you. Why are you not moving? Oswald. Well, Drew, why would you do that? Well, I told him to get in trouble. I'm good. Okay. Too many windows. Close all the windows. All right, there we go. So today's our little nuclear chemistry lesson. Not too long, because we aren't going to spend a whole ton of time focusing on nuclear chemistry. We're going to be moving into organic and biological chemistry pretty soon. So that will be a whole different ballgame. And then did you guys turn in your homework?
Not yet.
I think you were supposed to. I'm double checking because I know the other group was supposed to. So let me make sure.
I might have left my binder at home.
Well, you can always send it.
Yep.
That's how it works. There we are. Got to go through 100 things to get there, but hey. Yep, you're turning it in today, so be sure you do. And some of you missed your test, so be sure that you finish your test. All right, so here's y'all's lesson for today. I will enable content. Thank you. So nuclear chemistry, huh?
I think I did the test.
I don't remember, but if you didn't, you'll find out because when I hit that little email test is missing thing, it shows up. The little email test is missing, blah, 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 reassign. Some of y'all just forgot it, I think, because it was spring break, and that happens. So I will send it out to everybody again as a reminder. Alrighty, so atomic nuclei, nuclear stability. So when we were talking about these nuclear reactions, we're talking about messing around with the nucleus of an atom, which results in fission, right? So atomic nuclei have what we call strong nuclear force. Now, those of you who did physical science last year may remember there was a strong nuclear force and a weak nuclear force. We're really only focusing on the strong one here for the purposes of chemistry. So basically what you've got is if your atom's really big, most of it's the electron cloud, right? In the middle, very, very, very tiny is the nucleus. Now, this is real easy. Say the word nucleus. Nucleus, right? Nucleus. Now say nuclear. Don't say nuclear. I'll disown you. Nuclear is not a word.
What about nuclear?
Nuclear. Nope. nucleus, a lot of people get the nuclear thing going. And I was telling the younger group, it made me insane because George Bush did it every year he was in office. Anytime he had to mention the word, he said nuclear. And I'm thinking, all right, it's a common mistake, but you've got people that work for you. Why are they not fixing this? You sound totally ridiculous. Nucleus, nuclear, nuclei, all those are easy to remember. And if you just think, well, it's new information, I hope it's clear, then it's nuclear. So in the middle of your atom, you have an itty bitty nucleus, right? And then it's filled with particles that together we call nucleons, right? And they're the protons and the neutrons, which you guys know. All right, so if you have two positively charged protons, they're going to want to repel each other. Just like taking two positive ends of a magnet and trying to stick them together. Doesn't work real well, right? The magnet pushes away. Same thing happens here. So what keeps the nucleus from flying apart is that there are neutrons tucked in between them all. And there's a force going on there that we call strong nuclear force, which is really, really strong, but it spans a very, very small distance because it's in the nucleus of an atom, so it's itty, itty bitty. Strong, but doesn't go very far. So it's very short range attractive force between nucleons. All stable nuclei except hydrogen 1 contain at least one neutron to overcome the electrostatic repulsion between the protons. As the number of protons in the nucleus increases, the number of neutrons needed for a stable nucleus increase even more rapidly. Too many protons or too few neutrons in a nucleus result in instability. Okay, so this is where we start getting into radioactivity, which is the instability. I'm not sure what that was, but there we go.
It's like Scooby-Doo.
I don't know what it is.
Scooby, is that you?
He did something creepy. So,
He hit me with a pillow and he started laughing.
Oh, no, it's the rainy black suit.
Oh. You hit me with a pillow here when you have
so
time.
mass defect. Now, this is something I want you guys to understand, mass defect. From your reading, did anybody gather, can anybody describe mass defect, or what did you gather from it? Or do you remember? You probably read it before spring break was over, because you're smart people. You probably didn't want to have work over break. I'll help you out. All right, so your mass defect is this. If I give you a bucket, or let's say a basket, and some apples, and we put the basket and the apples on a balance, and we decide that the mass of the basket and the apples is 2 kilograms, okay? Not a lot of apples, whatever. So we have the basket and the apples, 2 kilograms. If you took the apples out and the basket out and weighed them all separately, what would the mass be? If you weighed them all separately and then added all those together, you would still get 2 kilograms, right? That makes sense because all the different parts should add up to the whole. That doesn't work in an atom. It doesn't work in an atom because some of that mass is actually converted to energy. So when the nucleons combine to form the nucleus, some mass is actually lost, but it's never really lost, right? It's converted. So it's converted into energy. So here's an example in this picture here, this graphic. It's showing you got, I don't know if these are neutrons or protons, but blue ones and green ones, and then these are obviously electrons. You have,
that looks like a helium.
yeah, very good. And then you have this same right here, your same AMU. You should expect this number to be the same if you took it apart, right? That is not the same. It's converted to energy. So that's what you have to remember is that little bit of energy though, which it seems like a little bit of energy because it's a tiny, tiny, tiny amount of mass that's converted, right? But it's actually a massive amount of energy because it's the energy required to fuse the nucleus. And so obviously if you split the nucleus, it's going to get to be an equally huge amount. And you've seen what happens when you split a nucleus, right?
Big boom.
Yes.
That's a, yeah.
Mm-hmm.
Very simplified way of saying
It's a very simplified way of putting it.
But
So nuclear binding energy, here's where we get Einstein's famous equation. All right, so nuclear reactions, like chemical reactions, are accompanied by energy changes. All right, makes sense. The energy changes in nuclear reactions are enormous compared to those of even your most energetic chemical reactions. Your most energetic chemical bomb or whatever that you could possibly think of making is not going to be anywhere near as big as a nuclear reaction will be because the energy change, the energy produced is so great. All right. So in a typical nuclear reactor so large, they result in a measurable change of mass, which is what we talked about. Now, we've done a ton of chemical reactions this year, and our mass was consistent all the way through. We even did experiments to prove it. Remember, we did experiments to prove that, the same mass would result on the other side, despite what happened at the beginning. There's a whole law of conservation of mass business, and we're like, ta-da, look, we did it. And now I'm telling you, well, sometimes on a rare occasion, you're not going to see that mass show up on the other side because it's going to get converted to energy. So this is where Einstein comes up with the concept of the relationship between mass and energy. So what's his most famous, well-known equation?
E = mc squared.
Right. Okay. So this makes perfect sense. You got your mass and your energy, and he termed those as the mass is the m and the energy is the e. But he knew or figured that you could put the speed of light into this equation. What in the world are you guys doing? Quit, Alex. Jeez. All right, y'all. Y'all are like 7th graders. Anyway, actually, my 7th graders don't do that. There we go. So anyway, you express your energy and your mass in joules, kilograms, whatever. If you've never watched a documentary or even a YouTube video on Einstein himself, pretty fascinating dude.
Einstein was awesome.
Pretty fascinating dude. Did he have any offspring, children? Did he produce any heirs? No children. No children. No, he had nieces, nephews, and things of the sort, but no children. Where did he practice physics in the United States when he got over here?
Somewhere on the eastern.
Yeah,
seaboard.
Princeton, in New Jersey. Yep, you almost said it. Yep, Princeton. So he was actually there, working in their physics department. Not so much teaching as just being able to do what he did. Kind of gave him free reign. But if you go to Princeton, you can visit the house he stayed in, and all of that. Now, I read a really interesting article about when he passed away. Well, first off, he's Jewish, so they bury their people way more quickly than like Christians who will sometimes wait a week or whatever to get funeral underway. So they had to hurry him on out the door, but they were very hush hush about it because they didn't want there to be this huge, crowd of people. And it's interesting, very interesting to read about who he was, what he did.
He was also really funny too.
Yeah, quirky.
He had a quote that was like, if you're driving safely in a car with a pretty girl, then you're not giving the pretty girl enough attention.
He was full of all kinds of odd quotes, and he very likely had learning challenges like dyslexia or ADHD or things of that sort, maybe on the spectrum. I mean, things that today we recognize that then we're just kind of like, wow, he's a weird dude, but he's a weird and genius dude. How anybody, thinks to stick the speed of light in here and suddenly produce an equation that makes sense, fascinating fella. So you get to nuclear stability, and then there's this whole band of stability thing. Now, I want you to understand what this is for the sake of knowing that you can use it as a predictive tool. I don't expect you to be using it all the time, right? So certain isotopes are going to be more stable than others, which makes sense, right? And their stability is determined by the ratio of the number of neutrons to the number of protons in the nucleus, which also makes pretty straightforward sense. So at low atomic masses, the ratio is usually 1-to-1, and it's about, I cannot read, at about an atomic mass of 20, it starts to increase until it gets to about 1.5-to-1 for heavy elements. And that's due to the fact that the higher numbers of protons and need more neutrons in order to affect that repulsion and keep it from happening. So there are all these rules that they use for predicting it. And they use this ZN line and all of this stuff. And they call this ratio the band of stability. So you probably saw, or you may have seen something like this before, but this shows you this little dark line here. This shows you where the stable nuclei should lie if you graph the neutrons on the Y and the protons on the X-axis, okay? And then these ones on this side are more prone to this type, this beta negative decay, bless you. The ones here are more prone to the beta positive decay, and then up here is the alpha decay. So they've managed to plot them and see this sort of result, which is good because it means this type of pattern is predictive. And that's what you should know, that it's a predictive pattern. So nuclear change, what does that mean? So we talked before about law of conservation of matter, right? So if you have an atom of a particular element, is that atom of that particular element always going to be that same element? Always going to be an atom of that same element? Now, well, not necessarily, because that element, even if it's pure element, is not, I'm not talking about like chemical reactions that could happen that could change substances from one to another, or it could combine and make a compound, or an ionic compound. I'm talking about the fact that when you have radioactive decay over time, an element can actually change into an entirely different element. And when you see it with the elements with the lower numbers on the periodic table, you tend to see the ones that we use frequently for stuff like radiocarbon dating, right? Like carbon-14 is a big one. But the big heavy ones, they're the ones that we use for nuclear power, nuclear weapons. So there is, this video is pretty helpful. So this guy, well, this lady, no, was it a lady? British somebody.
How do you know
dude,
if an atom is stable?
Dude, there you go.
In this video, we're going to learn about radioactive decay. An atom is composed of subatomic particles called protons, neutrons, and electrons. Positively charged protons and neutrons with no charge from the central nucleus. Negatively charged electrons orbit the nucleus. For more information on atomic structure, watch this video.
We got that down.
A strong nuclear force holds the positive protons and neutral neutrons together in the nucleus and is what determines if a nucleus is stable. In stable nuclei, the force is strong enough and brings sufficient energy to hold the nucleus together permanently. Most of the nuclei formed during the Big Bang nearly 14 billion years ago are still in existence today, but not all nuclei are stable. Unstable nuclei either have too many protons or too many neutrons, upsetting the strong nuclear forces. Unstable nuclei try to balance themselves by giving off the excess proton or neutron. This is radioactive decay. Unstable nuclei are radioactive and emit radiation. There are three types of decay: alpha decay, beta decay minus, or beta decay plus. Alpha decay is the loss of an alpha particle. An alpha particle is made of 2 neutrons and 2 protons. They have a mass of 4 and a charge of +2. When an atom loses an alpha particle, the mass number decreases by 4 and the atomic number decreases by 2. A new element is formed that is 2 places lower in the periodic table. When an isotope has too many neutrons, it decays by beta minus decay. A neutron changes into a proton and an electron. The proton is retained by the atom, while the electron is lost. The lost electron is high energy and is called a beta particle. By losing a neutron whilst gaining a proton, the mass number of the atom remains the same, but the atomic number increases by 1. A new element is formed that is 1 place higher in the periodic table. When an isotope has too many protons, it decays by beta plus decay. A proton is converted into a neutron and a positive beta particle called a positron. Positrons have the same mass as electrons, but the opposite charge. By losing a proton but gaining a neutron means the mass number stays the same, but the loss of a proton means the atomic number decreases by 1. So how do we know if an atom is stable or unstable? We can determine whether a radioisotope is likely to decay and what type of decay is likely to occur by looking at its position on a proton-neutron NZ graph. This graph shows the number of protons on the x-axis and the number of neutrons on the y-axis. This is the stability line. If a radioisotope lies left or right of this line, it is unstable and likely to decay to become stable. A radioisotope that lies to the left of the stability line has too many neutrons and is likely to undergo beta minus decay, so give off electrons. A radioisotope that lies to the right of the stability line has too many protons and is likely to undergo beta plus decay, so give off positrons. If particles have a high number of protons, usually more than 82, they are likely to undergo alpha decay. In this video, we have learned that unstable nuclei either have too many protons or too many neutrons, which upsets the strong nuclear force holding the atom together. Unstable nuclei try to balance themselves by giving off the excess proton or neutron either through alpha, beta minus, or beta plus decay.
If you like the video, give it a thumbs up.
Yeah, she goes. Yeah. So you had that band of stability, right, that we saw going through the middle. And as you notice that NZ, you see that NZ line, it was perfectly diagonal up the center. So that would be equal number of protons and neutrons, right? And you saw that stability line was slightly started along that NZ line and then it kind of curved to the left. And that's exactly what they meant about protons and neutrons having a 1-to-1 ratio and the lower, the not quite as heavy elements. And then as it gets heavier, it becomes more like 1.5 to 1, which you can see really clearly if you look like right. Where's the thing? Where's the thing? Show me the thing. That thing. There it is again. So here's your band of stability right there. And obviously this would be right up the middle, right? This would be perfectly even ratio. So you can see that 1-to-1 ratio kind of changes to that 1 to 1.5 as you go up. Oh, I'll go back.
So the orange is the stable because it's on the right side of the stability line.
The line is stable.
The line is stable, but okay.
Mhm.
Okay.
Everything that's not black is
Yep.
unstable.
The line is stable, and this side is more likely to have beta negative decay, this side beta positive decay, and then way up in here you get the alpha. So that you can predict is the whole point of that, of learning about that graph, is that it exists and you can use it to predict. Oh, move on, move on. No, move on. So Adam, he's going to talk and I have to shut him up in a minute. An atom is stable if the forces among the particles that make up the nucleus are balanced. If it's unstable, we say it's radioactive, right? And then instability of an atom's nucleus may result from excess of protons or neutrons. All right, so NZ and change. So remember that nuclear stability is a concept that helps identify stability of an isotope. Two main factors are the stability of the neutron-proton ratio, which we just saw on the map. And then what's an isotope? It's an element with a different number of what? Say it.
First, the brownie point, it's supposed to be an isotope.
Speaking of brownie points,
Yeah.
how many do we have?
I don't know. It was in your last letter. I'd have to go look.
Oh,
You've got a lot. Yes.
speaking of brownie point as well. I can probably find it on my phone, but on the test, the 17.
You found one?
Either 10 or 11. I couldn't remember which one it was.
Yeah.
On the bottom, it had a minus exclamation mark instead of a -1.
Ooh, okay. I'll have to look at that. Thank you. There we go. Did you catch that one, Alex? I don't know if you did or not.
I saw it and I'm like, what the?
Somebody may have caught it.
I remember seeing an exclamation point in place of a 1 and 1 thing.
Oh, there you
I
go.
can't
Oh,
remember
yeah, I
if
think it was
that's
in the question as well. I can't remember.
Neutrons.
So yes, neutrons is the answer, Cole. So right, an isotope is an element that has a different number of neutrons than you should expect it to have based on the periodic table, right? And then these are all of these little factors you can use if you're going to do calculations, which I'm not going to expect you all to do. But the principal factor for determining whether a nucleus is stable is the neutron to proton ratio. Elements with, here you go, Z less than 20 Z. Remember, Z was proton, greater than 20. Yes. What'd you see now?
Every element has a proton, neutron, and an electron. That doesn't hurt.
No, I copied this from something, so I didn't type it, but helium, hydrogen is missing a neutron. So
yes, so not
yep.
every element. And
yep, you're right. Good call. I didn't
And
notice that
every
one.
element doesn't have just one. Each one has.
Yeah, it
two
should say
numbers.
at least A. Okay, yeah. I didn't type it, like I said. All right, so then you get, when you have the ratio of 1 to 1, they prefer the same number. And then when you start getting bigger, like numbers 20 to 83, those are the heavy
I
elements.
found the brownie point.
And you go to 1.5 to 1. What'd you find now?
The number of electrons is equal V. That is supposed to be equal to the.
Where are you?
Else it is in rock.
Where are you? Which one are you in?
It's
Which bullet point?
the isotope one. It's third line.
The number of electrons is equal to protons. That's fine.
The number is equal to protons.
Oh, equal to. I see.
There's no two.
Yes, or it should say equals. Correct. All right. Well, my copying source was cruddy then, apparently. So as you get closer to the 1.5 to 1, it says the reason for this difference is because the repulsive force between the protons, the stronger the repulsive force, the more neutrons are needed to stabilize the nuclei. So neutrons help separate the protons from each other in a nucleus so that they do not feel a strong repulsive force from each other. And this is, if it will go to the next sheet, Cole. Yes, Alex?
I think there might be a comma missing from somewhere. To determine the number of neutrons in an element, I think after that it's supposed to be a comma.
Which one are you in? Which bullet?
Still isotope.
You're still in that one.
To determine, move on. Second to last line will have the element that.
Probably should, but as I said, didn't type it. I would have put it in.
Type it.
Yeah.
She said that earlier.
But I should still catch them. All right, so N and Z change. Here's another version of that same graph. The delta stability makes it easy to determine where the alpha, beta decay, and positron emission are going to occur. So this is some information on alpha decay. And it talks about how it's located at the top of the line because the alpha decay decreases the mass number of the element to keep the isotope stable. Yes. Did you have a question?
No, I figured it out.
Okay. And it's accomplished by emitting an alpha particle. And then your beta decay accepts protons. So your beta negative decay accepts protons. So it changes the amount of protons and neutrons. The number of protons increase by 1 and the neutron number decreases by 1. And then your beta positive decay, this is your positron emission. And electrons capture, positron beta positive emission, I cannot speak today. And electron capture is when the isotope gains more neutrons. So I don't expect you to memorize the graph or anything. I want you to know it's a very good predictive tool. So it says, as with all decay pathways, if the daughter nucleotides are not on the belt, this being the belt, then the subsequent, then the nucleides.
I was gonna say, there's no T.
Oh no, nucleides are not on the belt, then the subsequent decay pathways will occur until the daughter nuclei are on the belt. So your daughter nuclei would be what you're starting with. If it's not on this belt, which is where you're stable, the decay is going to occur until they do land on the belt, which means it's stable. Does that make sense? Ethan, a little bit? You look like I don't know about this. So I wanted to show you this one. This balancing a nuclear equation is one, a balanced nuclear equation is one where the sum of the mass numbers, the top number in the notation, and the sum of the atomic number balance on either side of an equation. So nuclear equation problems will often be given such that one particle is missing. So I wanted to show you how this works, but I'm not going to expect you to do these. I still think it's important to know
All
how
right,
it
in
works.
this video, we're going to do some practice with balancing nuclear reactions. This first one, and beryllium-9 plus, and this we would say is helium-4, but really this is an alpha particle, 2 protons and 2 neutrons. It's going to make carbon-12 and something unknown. Well, it's important to note that whatever I have for mass here, I need to have at the end. Same thing for down here. So I know that 9 and 4 is going to add together to be 13. So on the other side, I have to have that as well. So I need to account for something over there that's going to be at least a mass of 1. Then I know that I have 4 protons here, 2 protons there, so 6 there. So I don't need to do anything to take care of that. I'm going to put 0. And here I have a mass of 1. But 0 protons, charge of 0 as well, that's going to be a neutron. So that's going to be my missing part for this nuclear reaction. That would make it a neutron. So next up, I have polonium-212 is going to break down to form an alpha particle, and the remainder of it, that's what we're going to solve for. So I have 212 here, and this needs to be the same over there. So that's going to be 208. So 208 plus 4 gives me 212. And I have 84 protons here, 2 over there. So I need to count for that. So I'm going to have 82 protons over there. 82 means that that's my identity of lead. So I'm going to put that there. So that is going to be lead 208 is going to be what I solved for right there. So into the decay of polonium, alpha decay means it's going to release an alpha particle plus lead 208. Here I have Einsteinium plus an alpha particle is going to release a neutron plus something unknown. So I have 253 and 4 there. And so it's going to break down and release a neutron. So I know that that total on the left is going to be 257. So on the right, it needs to be the same. But here it's going to be 256 because I already lost one with the neutron there. I have 99 protons plus 2 means I have 101 on the left. On the right, I don't have anything that's going to affect that at all. So that's going to be 101. So 101 is going to put it as MD Mendelevium. So when Einsteinium gets hit with an alpha particle, it's going to release a neutron and Mendelevium 256.
He has so much fun with this. He goes so fast.
Promethium plus something is going to break down to make.
See if you can follow his process.
So neodymium 142. So I need to figure out what's the difference there. Well, I have 142 on the left and 142 on the right. So the mass is going to remain the same. But the proton number has changed. It's come from 61 to 60. So it's actually decreased by 1. Well, the only thing that can do that is a -1 down there. That's going to represent an electron. So we had electron capture right here, where one of the protons got turned into a neutron. So the mass didn't change, but the number of protons did. So that's why it's changed identity into something else. So that's an electron. Beryllium 9 plus an alpha particle, helium 4, is going to make something plus a neutron spit out from there. So I know I have 9 and 4, so that's going to be 13 right here. To account for that difference, I'm going to put 12. I have 4 plus 2 on the left and 0 over here, so that's going to be 6 right there. I know that's going to be carbon, so that is going to be carbon 12 plus a neutron is released. Here I have sodium 22 plus something is going to make neon 22. So you'll notice that the mass number has not changed, but the protons have. So I know it's going to remain 0, and I go from 11 down to 10. So we know that that's going to be a -1. So this is another case of electron capture, where a proton is going to get turned into a neutron by absorbing an electron. That's going to be my unknown.
This guy's so fast.
Yeah, he apparently really enjoys that. It's like his favorite thing to do.
I don't get that.
Yeah, good for him.
Good
All right, in this video, we're going to
No, go away. So finishing up nuclear change, we have nuclear fission. What happens in nuclear fission? Your nucleus does what? Breaks apart, right? So nuclear fission in physics and nuclear chemistry is the concept that during radioactive decay, you've got a nucleus that's going to split into 2 or more lighter nuclei. All right. The opposite of fission would be what? Fusion. If you had 2 hydrogens that fused, what would you produce?
Not quite a helium.
You're right. Where does this happen? Constantly, all the time. In the sun. There you go. Yep. So that's what we're doing.
Helium.
Yep.
You need 4.
Right. Yeah, you need 4 and then you get 2. So nuclear fission is a subdivision of a heavy atomic nucleus, such as that of uranium or plutonium. These are all different definitions of nuclear fission, into 2 fragments of roughly equal mass. And it's accompanied by a release of a large amount of energy. Well, obviously a large amount, oh, you found some other typo from something I copied.
Nuclear fission, subdivision of.
She didn't.
That's correct. That's in a positive phrase. Nuclear fission, comma, subdivision of a heavy atomic nucleus, comma. So that's in a positive phrase in that case, because it's redefining.
Life is just to capture every single brownie point without fail.
Telling you, man, he knows how to win over the teacher.
Oh boy, wants to.
So fission occurs when a neutron. Now this is another thing to understand. So when fission occurs, it's because a neutron has slammed into a larger atom, and it causes all this excitement, and it splits that atom into smaller atoms, and then those have neutrons that are now free, and those slap into other atoms, and this causes a chain reaction. So when each atom splits, a tremendous amount of energy is released. And that's because, as we said, that strong nuclear force is a ton of energy, but it's holding everything together. And that little bit of energy was converted from mass, right? That mass converted to energy. And that doesn't happen all the time, every day. That's a that's a really special process that's going on there. And it's a ridiculous amount of energy because we did how many things this year? That never happened, right? That's not something you're going to do unless you go into nuclear chemistry that you're going to see every day. So uranium and plutonium are most commonly used in reactors, and that's because they're easy to initiate and control, comparatively speaking. And then the energy released in fission by the reactors heats water, produces steam. Steam spins a turbine, produces electricity, carbon-free electricity, as they point out. So here's a good graphic for nuclear fission. And then I have one that actually moves. So here you got this guy's the incident neutron. He's bumping along, slam, smacks into this. This guy blows up, kaboom, right? And then you get all these new incident neutrons that create this chain reaction. And it keeps going to a certain extent, right? There's a great little GIF. Where's my little GIF? Isn't it here? I thought it was on this page. Oh, it must be on the next page. Anyway, so this was an infographic I had to split in two to fit it on here. So everything on the left is fission. Everything on the right is fusion on both sides. So here's this is fission, it's split. There's fusion, it joined. And this just shows you the type of fuel most commonly used. Heavy stuff, light stuff, right? Used for nuclear fuel. We got a little helium spinning over here. And then energy production, and I love this one, under development. We don't have that fusion thing down, right? Like, we haven't quite gotten there. Yeah, if you've seen, which one is it? Is it Back to the Future 2 when he comes back and he's got that Mr. Fusion on the top of the car instead of Mr. Coffee, and he like sticks random food in it and he gets energy from it? Wouldn't that be great? That was supposed to be 2015, but we missed that. And then this is the thing that I think is most interesting. So your energy from fission is 1,000,000 times greater than your typical other energy sources. So that would be hydro, wind, coal, that sort of thing. But your energy from fusion is 3 to 4 times greater than fission. So if we can harness that successfully and safely, that's a lot of energy. That's a ton of power. Think of what you could do with that much power and energy, like worldwide.
Take over the world.
Yeah, you could provide for the world is what I was thinking. But, never mind me. Yeah, there are a couple of different ways you could go about this. But, you really, truly could provide energy for just pretty much everybody if you figured out how to get that done. So that's something that it would be great if your generation figured out. Here's my GIF. I love this GIF. It's perfect. Like, watch me. Boom, boom, boom. It's like playing pool. You ever play pool? Same thing. It's like a billiard game. There's that incident neutron. More incident neutrons.
I play pool wrong. So.
Oh, it doesn't do this when you do it?
No, because I just throw the balls.
I'm not very good at it myself. My dad's like a master, but I'm not.
Yeah, it's just I just picked up the table.
So this is the concept of a chain reaction, which I think everybody here understands the concept of a chain reaction. It's the movement of energy. It just keeps going from one point to another, right? So you've got a process where your neutron is released in fission, produces additional fission, and at least one further nucleus. And the nucleus in turn produces neutrons, and the process repeats. To maintain a sustained, controlled nuclear reaction, for every 2 or 3 neutrons released, one must be allowed to strike another uranium nucleus. So this is how they do it in nuclear reactors. If the ratio is less than 1, the reaction is going to die out. So if it's greater than 1, it'll blow up uncontrolled. So they've figured out how to get the ratios correct so that the chain reaction continues without either stopping or getting out of control. You are in a special place today. I don't know what the deal is. So how do we use nuclear chemistry? All right. There's some very interesting ways we use nuclear chemistry. So this is one of my favorites. I have to admit, I indulged a bit here. Half-life. Somebody tell me what a half-life is. Do you know? Do you remember?
The amount of time it takes for half this.
Yeah. There you go. Okay.
Particles,
So
whatever you want to call them.
yes, so I had to go with these memes because they made me giggle so much when they actually came out. If you remember the Starbucks unicorn frappe,
Oh God, that thing.
right? There were great memes when it came out. Do all these people drinking the new Starbucks unicorn frappe realize they have but a half-life, a cursed life from the moment the drink touches their lips? And you have slain something so pure and defenseless to save yourself that you will have but a half-life, a cursed life from the moment the unicorn blood touches your lips. So anyway, those are good. So your half-life it's a constant thing in a specific radioactive isotope, and it's the time it takes for half of the isotope to decay. And it's constant and it's exact and it's very specific. So it's very predictable, Alex. It's very predictable. So that means we can use it. And for example, carbon-14, what do we use carbon-14 for? Do you guys know? I'm sure you've heard it. Radiocarbon dating. So what is that? How's that work? You guys know? So yeah, they use it in geology. They use it in archaeology.
Paleontology.
Yeah, so it's so exact. Radiocarbon dating is so exact because half-life is so exact that they can predict the age of a material, an organic material. It has to have the carbon in it, right? And all living things do, because all living things are carbon-based, which is where we're heading into our lessons in the next couple weeks. You can tell exactly how old that artifact is if it's got carbon in it. And it's fascinating because they can get it down. They've gotten really good. And with some of them, they can get it, like things that are millions and millions of years old, they can get down sometimes within a couple of centuries or decades. And then things that are, you know, a couple thousand years old, sometimes they can get it down within a year or so, which is really, really cool. So here's radiocarbon dating and some graphics for you. So it's a method that provides objective age. Now, objective, what do we mean by that? If you guys remember from Earth Science, when we talked about indicator fossils and things, like you're digging through the layers of dirt and you see, oh my gosh, it's a whatever, something, something fossil. Okay, well that something, something lived during this time period. And because this other thing is found in the same layer of soil, it has to have been from the same time period, right? That's one way that we do it. And another way we do it is, whoa, is he really low today? That might be the guy. We have a guy around here who's he's a pilot, but he does trick stunt stuff. Like he'll take his little plane up and cut the engine off and let it spiral down. And he does it over our house all the time. It's kind of freaky. So it's very objective. There's no subjectivity. It doesn't matter if the soil's been, say you have a rock, okay? And a mountain range, all right? And you found fossils in the mountain range, but the mountain range has been squished over time, or a glacier moved things. That can all affect your dating estimate, right? So in this case, it's completely objective. And age could be estimated by measuring the amount of carbon-14 present in the sample and comparing this against internationally used reference standards. So this shows you here at the bottom that it's a measurement of the beta decay in a buried piece of wood. So at 100%, at zero, it's going to have 100% of what it started with. And then 50% of it, we know is 5,730 years. And at 25%, they know it's exactly 11,060 years. And 12.5%, 17,000. See, they're really good at getting it pretty darn exact. So here's an example here. They've got this Moa bone, and they clean it, and then they take a sample, and they put some acid in it, and they freeze dry it, and they mix it up with some stuff, and then they get benzene. Oh, benzene's coming. This little dude right here was the bane of my existence for all of organic chemistry in college. Benzene rings. Oy. All right, and then they're adding more stuff, and you get down here, and they put it in a spectrometer. Do you know what a spectrometer is?
Sure don't.
Okay, spectrometer is cool. So you can take a chemical in such a small amount in a little syringe that when you inject it, it actually sort of aerosolizes, and the machine will produce like a color band. Remember, like when we looked through the little spectrometers earlier this year, and we could see color bands. Do you remember that with we did it with, what was it, sucrose and something else?
Yeah.
Yeah. Okay, same kind of thing, but it produces basically a fingerprint of exactly what's in there. Really fun. And they're weird looking. They look like a box with like a little tiny, like a rubber diaphragm looking thing that you just kind of stick it in, and then it spits out the results. They're very cool. And then it can give you the exact date, or really pretty close to the exact date. They've gotten really, really good. So what are some practical applications of radioactive isotopes beyond carbon-14? This gets super fascinating. What are some that you know of? Do you know of any? What do you think?
Nukes.
Nukes. Okay, there's that. And power. What else? Anybody ever dealt with anything radioactive? I bet you have.
X-rays.
Okay, yeah. All right, so it's not just a few things. It's a ton. This is only one of like 3 pages, I think. So I'm not going to read them all, but if you look, you know, here's the obvious one. Here's carbon-14. We just talked about that. But chromium, cobalt is a tracer. They use it for pernicious anemia. They can use gallium in medical diagnoses, iodine for treating thyroid disorders. And then, dudes. And here's more examples of things, right? So look here, nickel 63 is used to detect explosives and in voltage regulators and current surge protectors in electronic devices and in electron capture detectors for gas chromatographs. All kinds of stuff. Phosphorus, selenium, radium makes lightning rods more effective. Who knew? Strontium in bone formation and metabolism studies, strontium 85.
I want to know how radiation makes lightning rods more effective.
Radium 226, look it up. I'm not sure how they use it.
Yeah, bro, look up radium 226.
Well, look, here's thallium 201, and they can use it for nuclear cardiology and tumor detection. I mean, we have found so many uses. Thorium helps fluorescent lights last longer, thorium 229. And then you got, look at the uranium 234, used in dental fixtures like crowns and dentures to provide a natural color and brightness. All kinds of things, right? All kinds of good uses. We have found many, many ways. So your homework, which you turned in, but I'm going to look at it with you anyway. You guys remember these? So what energy is emitted when a nucleus forms? Anybody remember what it was from your homework?
Radiation/mass effect.
Yeah, which is nuclear binding energy, right? All right, and then what was a nucleon?
Particle that's in a nucleus.
I just got it. Yeah, it's either a proton or a neutron. They make up the nucleus together, right? So they have a combined name that we're going to use now when we're referring to them together. So what is the high energy electromagnetic radiation produced by decaying nuclei? Okay, so this is where we go back to the little y'all. I see it. I see it. So this is where we get talking about gamma. Where do you have gamma ray? Where have you ever experienced gamma rays? Have you? I bet you have. No, I bet you have though. You ever been to the airport and done this scanner?
Oh yeah.
I don't like that one, but yeah, there you go. All right. How about what nuclear reactions what nuclear reaction happens when two smaller nuclei combine? That's where we get fusion. Remember, fusion are the small ones combining, fission are the larger ones splitting. So what's the difference between fission and fusion? Fusing is combining and fission is splitting. If you see a crack in a rock, it's called a fissure. There's the word again, right? And you know that if you're welding something, you're fusing it. So it makes perfect sense. And if you're fusing things, you're fusing the small, lightweight atoms like hydrogen. You're not fusing plutonium. That would be nuts. You're splitting those, right? So name the process that describes an unstable nucleus and emits particles and energy. That's an easy one. That was the answer from before. That's radioactivity, right? All right, so now critical mass wasn't in your notes because I'm not going to stick it on your test, but critical mass is the smallest mass of radioactive material needed to sustain a chain reaction. It was what we were talking about. It was the example given regarding nuclear reactors, how the incidence neutron needed to produce at least 3 other incidence neutrons. One of them had to hit a uranium in order for it to continue. And if you had too few, it didn't go. And if you had too many, it caused basically an overreaction or an out of control reaction. So your critical mass would be right what you need. That's the term, is right what you need. So what's half-life again? One of y'all said it before. Half-life, y'all got it. Come on. Half to decay.
Yeah,
My girl's got it over here.
With that.
And then what do you call neutrons and protons together? Yeah, there you go. Or nuclide in this case, either way. And then 2 types of nuclear changes.
Wait, is
Fission and fusion, we're saying.
nucleon is just a proton or a neutron, but you're not specifying, and then nuclide is the group.
Together, yep. Nucleon, if you're talking about one or the other. Y'all.
Isn't it easier just to say it's a proton?
I think it's easier to just go on a date. Keep poking at each other. You guys, are you gonna be all right sitting over there poking at each other? Oh my goodness. Do we need to swap places or something? Bailey's like, no, I don't want him next to me. I live with him.
I'm here because I'm trying to separate her and him.
Oh
That's why I'm
geez.
in the middle.
Well, they live together, so that's
I know,
fun.
That's unfortunate right there.
That's fun. Let's see. What have you got coming up? Looking.
He's looking at me.
Oh my gosh. Y'all are nutty. So looking at your work, you've got test 18. I'll go over that in a minute with you. Okay. And you're going to begin lesson 30. But if we take a quick look, I want to show you a couple things real quick. We are nearly wrapped up, right? We have very little left to do, which is awesome. Right. Your final project is coming. Next week's lab, I think it's next week's lab. That's the polymer lab. And we'll be making, you get over there? Huh? Yeah, we're actually going to make bouncy balls.
Wait, for real?
Mm-hmm, for real. I know, I'm cool.
Yeah.
What can I say? I am. I know, all of the above.
We like put on the collar.
No, but you do get to make a bouncy ball. And yeah, I know, but it's fun. Anyway, after that, our labs are going to get, we have one more lab at the very end that's going to be like, involving chemicals and getting all involved over there. But most, it'll be so next week's lab is this polymer. We're making balls, making toy balls. And then, so y'all don't lose your minds over there. And then we're going to have a DNA game lab, and it's like a card game. I don't know how to describe it to you. It's kind of like a card game. And then we'll do the isolation of DNA, which is the last thing. Alex, I don't like talking over myself, over other people. So the last thing we're going to do in this class is isolate DNA from two sources. One will be an onion. You can use anything, but the lab had an onion listed, and the other is yourself. You're going to see your own DNA. You're going to get to look at it, which will be really fun.
Yeah, what kind?
From your mouth.
Okay, I was like, if actually blood drawn out.
No, because I don't feel like picking Cole up off the floor, and he will pass out if there's blood involved. I mean, we all know this.
Oh, you'll pass it.
There's needles. Oh, y'all don't even know.
Blood?
Ethan, he faints, legitimately faints. It's okay. I mean, it's what happens. He gets it from my dad.
Unfortunate.
I don't think of the blood. Like, I think of needles. If
No,
I
no,
have
no,
a needle
no,
coming out of me, I'm like, oh gosh, no, here we go.
It's not, blood doesn't make me sick. It's the thoughts of your the best way to explain it is it's not like I see blood, oh, I'm gonna faint. It's like I don't like the idea of things going into my body. Like my body is the way it is, and I don't like the idea of foreign.
There you go.
Or taking it out too. It's uncomfortable.
So I wanted to show you all this while we're thinking about Cole passing out. These are the labs I have planned for next year, if everything goes well. If everything goes well, we get enough students in the class so that I can actually purchase all the things I want to purchase. Yes.
Is there a dissection?
Multiple. So yes, if I get my way, we'll dissect flour, which is not that exciting, but we'll do it anyway, and a chicken wing. Okay, but we will also do, this is what I have planned, earthworm, sea star, perch, frog, squid, fetal pig.
No.
Yeah.
Interesting.
Interesting.
Uh-huh. And
the squid. I will pass on the squid. That's the only one I'll pass on because I have bad experiences with.
we're also going to do, and this one you will love. We are going to do a DNA electrophoresis lab. And electrophoresis is the process by which they create those DNA fingerprints. You've probably seen them. It's like a series of bands next to each other. And we will be matching our sample against a sample from a crime scene to catch a criminal.
Oh.
Right up your alley. Yes, Alex?
A perch is a type of fish, right?
Perch is a fish.
Okay.
Yep.
Making sure we were going to cut up a fish.
I plan, and this all is if we get enough kids in here, enough students next year that I can purchase what I plan to purchase. Because I mean, we do divide up the lab fees, obviously, but there's a critical mass where you can start, getting what you want. I intend to get good solid microscopes for all 4 lab teams and a really nice kind of mid-range, but quality microscope that's a class microscope with a 15 megapixel camera that will give us really good digital pictures of stuff that we can look at class wide. And then I also wanted to get 4 really nice for you guys dissecting stereoscopes, which are really cool. They're 2 eyepieces instead of 1. And when you look into the stereoscope, everything is kind of more 3D, and you use it for dissection. They don't magnify as much, but they're really nice. And then I also wanted to get one for the class as well that will hook with the camera.
Did you say squid or octopus?
I said squid. You're still stuck on that.
I'm sure that thing just smells
Um,
I dissected a shark at some point. I don't
So
know how to have
I
it.
intend to get our specimen, our dissection specimens from Carolina Biological. They have their own, so BioPerm is like the formaldehyde mix that is typically used for preserved specimens, but Carolina Biological has one they call Perfect Solution, and it's supposed to be less stinky and keeps natural colors in place longer and sort of less disruptive to the preservation process. I have yet to have experience personally with it, but they really advertise it as this is a great alternative, and their prices for that are pretty good. So I think we're going to give the Perfect Solution a shot rather than the BioPerm in particular. But we're going to grow algae. We are going to, oh yes, it's going to be super fun. We're going to grow algae. We're going to look at, let's see, what's another fun one in here? We're going to check enzymes based on temperature. We're going to do some field research, at least 2 outdoor labs where one of them is an observation lab. Another one is it's a model natural selection lab where you are the predator. Yeah, should be a lot of fun. We're gonna follow the activity of termites. We may even get ourselves an ant farm. We'll see. And oh yes, and we're gonna do some labs where we're involving like our own nervous systems, like touch labs, and like, can you feel this? Can you feel that? That sort of thing.
You get to scare somebody like we did?
Yeah, I don't know about that one. That was fun though. I still have that video somewhere. And we'll work with Touch and Grow, where you guys are going to basically have some growth plates for touching a touch surface that you then put on the growth plate and see what you get next week. So agar plates. It'll be fun. Yes.
What type of predator will we be in the predator?
One that eats the prey that is dealing with the natural selection issue in the lab.
So basically any predator.
Mhm. And you will get to mimic Darwin's finches as well. So that will be fun, a fun lab. And we'll be doing some modeling with meiosis. Oh, and we'll be looking at regeneration in planarians. You know what planarians are? Do you remember? They're flatworms. They look cute. They look like little ghosts with eyes. They have little eyes, eye spots. But anyway, they completely, their body systems are such that they can regenerate. Like, you know, like a starfish can regenerate, or sea star can regenerate a limb, basically. These guys, depending on how you cut them, they can like grow new heads, tails. Yeah, they're itty bitty little flatworms. But you can look at them under the dissecting scope, and
How fast do you think it lives?
they don't hurt. They don't have a ganglia for that, so they lack the ability to feel pain. How much does what? Do you see stars?
How fast do you believe that like a starfish's
See stars? Yeah.
yeah, limbs will grow? Like, could we do it in one day? Would
No.
we, like-
Well, no, they won't go like that. And the sea stars we're getting will be preserved.
Sure.
Yeah, I mean, I can
Some
let me show you this real quick before we go over there.
actually can, like,
Regenerate.
no, it's like they could take their stomach and put it on the
Yeah.
Outside.
of their body.
It's pretty darn cool. That only works in animals with radial symmetry, and it's pretty daggone amazing.
Puke on something, except they're throwing their stomach
Yep.
on it and then.
Yeah, some frogs can do that too. They can literally puke out their stomach.
I don't think it's quite like that, but there still is. So just to show you our specimens, because they're in my spreadsheet, I can tell you exactly. Okay, I know. So to get to specimen down here, specimen, let me make it a little bigger so I can see it. So we've got lots of them. We'll need flowers, large seeds, lima beans, ant farm if we're lucky. Living specimen of aquatic plant, living specimen of B. subtilis, that's a culture. Living specimen of cholera algae and E. coli cultures. We'll have living goldfish specimens. We're not hurting them, we're observing them. And living leaf and land plant, living planarian, living protozoa, living S. epidermis culture, and living termites. And then we'll have preserved fetal pigs, perch, sea star, sea urchin, I forgot. squid. And then we'll also have some random seeds that we'll be using for stuff. So there will be lots of fun stuff. For those of you who are squeamish or not a fan of the whole dissection idea, there will be virtual labs in place of that. Yeah, if you prefer the virtual lab.
I do. Look it up.
You guys are nuts. All right, so I'm gonna kill my screen. I'm gonna kill my screen up here so that I can go over test. So if you want to have something ready, you may want to get it ready now. Kill that screen.
Test for what? Today?
Yeah.
Oh. I wasn't prepared for this. Hold on.
She's like, wait. Oh, wait.
I have to pay attention now. We're good.
No. I'm paying attention.
You're hilarious. I love it. So funny. Okay.
Dude, are you first of all, are you okay? Because you look so uncomfortable.
Yeah, I know she does. Bless her bones.
Are you like that?
No, don't say
Oh my gosh. All right.
it. Was from, I'll tell you.
Yeah. Test for chapter 18, which will be due next week. All right. You will need to know the following. It's not a very long one. It's a whole 5 questions and 13 points. You're going to need to know the difference between the mass of an atom and the sum of the mass of the atom's protons, neutrons, and electrons is a mass defect. And you're going to need to know what that is. Is it converted to energy when it was created, maybe? Because that's what we said. Yes.
Speaking of, would there be some questions that are like, type out this entire thing, sort of thing, like some
On this test?
Yeah.
You got one short answer.
Like,
and it's, so I'll get to it. So these are all pretty quick. These are fill in the blank or multiple choice or true or false until the last one. The last one's a short answer. So what does radioactivity mean? It means that what? The forces in the atom are balanced or unbalanced? Unbalanced, right? If you know that, then you're good to go. And what do you call it when you subdivide a heavy atomic nucleus? Fission. Very good. Y'all stop. All right. And then what's the amount of time it takes for half of the radioactive isotope to decay? Very easy. And lastly, your short answer will involve you listing at least, now listen, because you probably want to list it. It says list 3 practical applications for radioactive isotopes. And then it says 1 bonus for each specific radioactive isotope you can link to a specific application, up to 3 bonus points. So you can say we use radioactive isotopes for healthcare and energy and dating fossils. But if you can tell me which isotope goes with those, then I'll give you a bonus point for each one. Yep.
And this would be in the slides.
It's in the slides. Everything's always in the slides. I try to keep everything on the tests in the slides. So you can always just look back and do it. One last thing, I told the earlier group, and I should tell you all too, just for the purposes of lab, but Alec has gone back to public school. So he will not be with us anymore, but he does still have access to all class materials because his mom is big on you should learn for learning's sake, and he's already started the class. So he may be doing it on his own. And I did tell him ways to go about finishing stuff on his own if he cared to do labs on his own or whatever. But he still has access to the forum, and he still has access to the grade book, although he's not being graded anymore, if that makes sense. So anyway, he went back to public school, which was the plan all along. He's just, time was good. She thought he was ready to go, so he has gone. That's that. And I think most of you guys have given me your final, no, not all of you have, final project topic. That's due by tonight. I think it's due by tonight, or is it already due?
I think what's the final product topic?
The topic of what you're researching. You guys are doing silver. This is done.
I was just making sure that I got it.
So I don't have. Okay, let's see. Alex and Bailey are doing silicon. Abby's doing bismuth. Are your sisters doing it with you? You don't know. Okay, because they didn't answer. Shannon and Jack are doing sodium. Okay, and then you guys are doing neon. So your class is done. It's just the younger group that is. I'm still missing a couple. Yeah, you good?
Yeah.
All right, excellent. So that should be everything for that. And then, was there anything else I need to tell y'all? Final exam, oh, everything, just so you know, everything from now till the end of the year has been completed on my side. All of your lessons are written, the slideshows are done, the tests are all loaded, the final exam is completed. I just need to finish like quit hole punching in my key or whatever. Not anything that's gonna bother y'all. Really, hands are for hugging, not hitting. That's what they say in preschool, but now you can't say that anymore either. So anyway.
Hands are for waving.
Hands are for waving. There you go. Hands are for writing notes in class. So anyway, that's all good. And you know what? I can show you real quick in the next minute, just because you may be interested.
And cutting food up, because if you have to do food preparation, that's important.
Oh,
It's
sure.
also good for drawing.
Good for a lot of things.
You're a goofy dude, man.
There's only 3 people in Spanish Tuesday.
Yeah, it's going to be no, I think there's 5. Oh yeah, because Alex gone. That's right. So yeah. It's small because that's because Michael didn't come. That's what it was. I had one more in my head. So I wanted to show you, just so you, in case you didn't believe me, but you should. Where's my thing? I'm not even gonna comment, Cole, because you know. Gotta disconnect it and then reconnect it, because that's how it is. Disconnect, reconnect. Your dad's soaking up some sun out there. Good for him. So let me show you. Okay, sorry. Don't yell at me. Oh, I'll show y'all real quick so that you know we have it.
Are you lightning?
Oh gosh.
Are you lightning?
They're nuts.
You now get it? I didn't.
Yeah, a little bit.
Yeah, I think you do.
So for next year,
All my life.
did it go through or did not go through yet? Do the thing. There it goes. It says it's connecting, but it doesn't believe it.
I gotta go.
So for next year, it says it's connecting, but it's taking a year and a half to do it. Maybe it's lying to me again. Hang on. I love how it does that. Sometimes it's just like, I'm not gonna do what you ask. Try it one more time. Most of the time, it's really good. Oop. Oop. Thinking about it.
We should give Alex his own chair. Yes, we should.
Sounds good. You should.
Like separate.
It's good. But anyway, what I wanted to show y'all is that I do have for next year, here it goes, in case you were curious. Syllabus for next year is done already. So our lessons that's the syllabus in general, and it does go all the way to the end of the year. And the overarching preface, where we have the list of lessons, one on top of another, that is right here. And here are the lessons week by week, right there. So we'll be doing them in this order: biosphere, ecosystems, population, cellular structure, function, photosynthesis. These are the breaks. They're already in there too. Cellular division. Then we get into genetics, DNA, protein synthesis, heredity, genetic engineering, Darwin, natural selection, population evolution, taxonomy, which is one of my favorites. I love taxonomy.
Is that the labeling one or the stuffing animals one?
That's taxidermy. That would go with this book right here I have called Crap Taxidermy. If you've never looked at my Crap Taxidermy book, it is worth it.
I have not.
You should totally take a look at it sometime.
Yeah.
It's great. There you go. I mean, it's outstanding.
It's really bad taxidermy.
It's Crap Taxidermy. Yeah, it was like the perfect book. I had to get it because everyone needs this in their life.
Oh,
Look, Abby looks like she.
Abby, okay.
It's I mean, it says strange anatomy, anthropomorphic, like this little mole trying to blow up something. Anyway, it's a fascinating book. Yeah, those are my favorites. Anyway, Crap That's what it's
I
all about.
found that funny.
No, reaction.
So anyway, Crap Craft Taxidermy is a great book. No, taxonomy is categorization.
Okay.
Kingdom, phylum, class, order, family, genus, species. How do we categorize? And it tells you very much how things are related.
When Josh.
Then we get, hang on, Cole. Then we get the viruses, prokaryotes, protists, fungi, introduction to plants, structure and function, plant reproductive response, and then we get into invertebrates, and finally vertebrates and comparative vertebrate anatomy, that kind of deal. Animal biology and animal behavior, which is where we get to watch our termites at work, which should be really neat. We're going to be drawing lines and then seeing what they do when they cross the lines. Be really, really interesting. And then we get, at the very end is our human part, which could probably double as a health credit if anybody needs it. But we're going to cover all the main body systems. And it'll be, you know, digestive, nervous, musculoskeletal, integumentary, circulatory, respiratory, endocrine, reproductive, immune, and then you'll have your final exam. Yes, ma'am.
So this is not about this, but I saw while we were doing the thing earlier with the Chernobyl thing. I looked up on accident. It's a Chernobyl catastrophe. And it seemed like it was a totally different thing than the disaster.
I don't know.
I was looking at it, I'm like, okay, this doesn't look the same at all. So I was telling them, and
So
That's weird.
apparently they screwed it up so badly that
it happened
they screwed
twice.
that it affected time slash another dimension and screwed them up also.
Okay.
I said,
That's fascinating.
That is fascinating.
but they named it the disaster and the catastrophe, which looks like two different things.
It is. Yeah, that's interesting. So next year you will get a fall break in in September that aligns with the Forsyth County one. You'll get a week for Thanksgiving like usual, 2 weeks for Christmas. You will get a winter break that aligns with Forsyth County one. And again, it will again be a 2-week spring break. And that will be your year. And we'll go from August 10th to, May 17th. So basically the same exact schedule as this year, because this year was August 11th to May 18th or whatever. Next year's the 10th through the 17th. So it's basically the same exact thing. And then your grades will go out. So that'll be fun. And next year's final project, in case you are curious, because everybody always wants to know, it's actually a research paper. So this year went to the artsy people.
Oh no, that's not me.
Last year went to the handsy mechanical people.
I'm good at research as well.
This year goes to the research. Yep. So you're going to be able, it's very similar to what we did when we did sort of that bridged middle school version of biology years ago.
We're picking teams already.
These will be independent,
Okay.
but
Great.
but there will be different methods for presentation. You could, do a slideshow. You can just read it. You can do like a little kind of a speech thing if you want, but you'll be researching either a topic that relates to biology or a person that we've studied. Like you could do Einstein. You could do something off the wall like cryptozoology, which is, do you know what cryptozoology is? So cryptozoology is the study of like,
Fungus monster.
yes, the study of legendary animals. We don't really have.
Bigfoot.
Well, the thing about cryptozoology is that it specifically looks for scientific data to back the existence of these creatures. So it's interesting.
You know what cryptids are?
Yeah.
Yeah,
Like
so
Bigfoot.
it's basically just a study and trying to back up
Yep.
what's existing.
Yep, it's taking data that exists and putting it so that it supports your case that the chupacabra is real or whatever. I mean, you never know. Chupacabra. Or maybe you wanted to do something, and I said, like as an example here, you don't want to do something huge like dogs, because that's way too big. And you don't want to do life cycle of dogs because that's way too narrow. We know that life cycle of dogs. But if you wanted to do something about selective breeding for traits, how did the dachshund come about? How was the selective breeding involved? What genetics are involved in coat and color? All those type. You could do any of that kind of thing. Or maybe you want to research, something ecological. The Chattahoochee crawfish, which is endangered. All that kind of stuff. There's all tons of options. Tons and tons of options. The whole world's your oyster, basically, everything that's alive. So not the rocks and sticks, but everything else. So.
Kind of just stick.
It fell off a tree.
Only like 3% of the animals have ever existed or alive. Right
Yeah, it's very small. I don't remember the exact number, but it's very, very small.
Animals that used to be alive.
I like the one where and you guys may remember this from when we did that little, like I said, the little bridge biology. It was kind of a weird class. I tried to make it better than it was years ago. But we talked about roundworms in particular, and about how if you could make everything disappear except the roundworms, you would see like a shell of everything. I love it because they're on everything. They're just the microscopic roundworms in particular. They cover every surface of everything. It would be like a shadow of the world because it'd just be covered with little roundworms. So yeah, when you get thinking about it, it's like, ugh, yeah.
I remember at some point, like I was really, really interested in botflies. At some point.
Oh my gosh, those botfly videos
I know.
are like they're like the cyst popping videos.
when
It's
I
the
was
same thing. You
younger, it
get
was like-
sucked
I was
in.
like in
So we're
fourth or
good,
fifth
Michael,
grade.
Jack,
I was
Sydney.
really
I'm gonna let y'all go.
I knew
My favorite animal.
my favorite animal, dog.
Dog.
You wanna know what mine is?